Raphael Bousso from Berkeley.
Does this work? Yeah. Okay. So in a large landscape, most predictions are necessarily going to have to be statistical, but it's not going to be enough to just count how many vacua we have with property A and how many vacua we have with property B. Interposed between this sort of raw landscape statistics and what we actually observe are a number of important selection effects. First of all, cosmology may preferentially populate some vacua and not produce others at all. That will obviously be important. And then secondly, some vacua won't contain observers, and so they will not contribute to statistics of observed quantities. And the classic example of this, of course, is the cosmological constant. The overwhelming majority of vacua in the landscape have cosmological constant of order 1, and yet we don't see that because this landscape statistics is overwhelmed by entropic selection. Now, at a qualitative level, this sounds almost obvious, but the real challenge is in quantifying these effects. As Andre noted, there's the measure problem in internal inflation. There are problems such as characterizing what you mean by an observer when you talk about a large landscape. And I want to talk about progress hopefully progress in those directions. This is not a set of questions that is entirely new. Ever since inflation, people have worried about this. It'd be hopeless for me to really list all the literature. Here are some of the key players. There has been, of course, increased interest ever since we understood that in string theory we really have a large enough density of vacua to possibly explain the cosmological constant problem. And this is just a fairly random selection of very recent papers, and you can continue from there if you're interested. I'm going to talk about my own approach to this set of problems. And what I find attractive about it, among other things, is that it's really a single approach that can help us with both of the type of selection effects I talked about. This was developed in these two papers here, the second with Ben Freifogel and my student Yisheng Yang, and applied to a set of problems that I will present today in collaboration with Ronnie Harnack, Graham Cribbs, and Gilad Paris, and again with Yang. What I'll show in this talk is that this approach is quite predictive, and that so far it predicts the right things. That could change, and I think we have to keep testing it like other approaches as well. Since this is not a phenomenology conference, I should say more than just these two things to advertise it. I should say a little bit about motivation from perhaps some fundamental points of view. So, in fact, the approach that I'm going to follow comes out fairly naturally from lessons that we have learned a while ago in the context of black hole physics. Most of us are now convinced that black hole formation and evaporation is a unitary process, that the Hawking radiation carries away the same quantum state, let's say, of this star that made the black hole, but nothing much has happened to the star on the way across the horizon, and so the same quantum state is present at the same time in two copies here. And that is something that violates the linearity of quantum mechanics. So we seem to have a paradox. By assuming unitarity, we've got a violation of linearity. But as Preskill and Susskind and maybe others pointed out, this paradox isn't all that serious as long as we don't play God and pretend to be able to see the whole space-time. Because there's nobody in the space-time who can actually see both copies. There's no past light cone that contains both of them. Either you're outside, you see the Hawking radiation, or you're inside the black hole, you can see the star. So the natural conclusion, I think, from this is that we should get around this paradox by restricting our description of semi-classical space-time to regions that are of this causal diamond type. To regions that can, in principle, at least be observed without violating causality, that correspond to experiments that we can actually do. We certainly should expect our theory to tell us about any such region if it's complete, but it doesn't have to tell us about things that are going on scales that just don't fit into such a diamond. because they don't correspond to experiments you can do. And they seem to lead to actual paradoxes if we really insist on these descriptions. And it seems very hard for me to imagine that such a drastic viewpoint about global geometry could be contained within the framework of just black holes in asymptotically flat space. I mean, either we restrict to these regions or we don't, and so I think we should also do this in cosmology and explore what it leads to in the context of eternal inflation and predictions in the landscape. And what we'll see is that it actually simplifies and streamlines the problem considerably and gives us a number of interesting quantitative results. And I will present an example for cosmological selection, how the causal diamond affects this, and for entropic selection. Let me start with cosmological selection effects. So there the basic question that we ask is what is the probability for some vacuum X to be dynamically produced by cosmology? And then we can average over many vacua and so on, but that's the basic question. And Andre has already presented what is probably the conventional picture in this game, that of a global universe which is eternally inflating. You start out maybe in some de Sitter vacuum here. It's metastable, so it decays. It forms a bubble of some other vacuum, usually of a lower cosmological constant, which expands rapidly but not fast enough to really catch up with the exponential expansion of the parent. And so the parent actually continues to exist forever, and in other places decay into perhaps other directions in the landscape, and you get this sequence of nested bubbles inside of which other bubbles form, and as long as it's de Sitter space, it just keeps going. Sometimes you jump to lambda equals 0 or negative, in which case the process terminates. For negative lambda, you get a big crunch. But again, globally, there are always regions where you keep expanding. And as a result, every single vacuum in the landscape, I mean, unless it's just completely disconnected dynamically, is actually produced infinitely many times. And that's bad news, at least naively, because we were trying to compute the probability for it to be produced. And if everything's infinite, that's hard, so we need a cutoff to define probabilities. The most straightforward thing you would try to do first is to cut this evolution of the universe off at some finite time, and I've drawn a time slice. Maybe take the limit t goes to infinity afterwards, and just compare, well, the number or maybe the volume occupied by the red vacua to the number or maybe the volume occupied by the blue vacua. There's already some ambiguities here, but in fact, as Andre was probably the first to note, the ambiguities are much more serious than that, because you can choose different ways of slicing time. There's no preferred slicing in such a large inhomogeneous universe, unlike in each one of these individual bubbles, which are open FRW universes with preferred slices that stay inside the bubble. You can try to come up with relatively simple ways of generating slicings, and that's a very interesting and active area of research that Andre talked about. Some of the most straightforward ways of generating slices are already ruled out as a way of generating probabilities, because they predict things that are just in obvious conflict with the data. I promised that I was going to apply this restriction to causal diamonds to this problem, and so let's see what that does. Here I've picked the random world line. And of course, as I said, this world line is eventually going to end in some terminal vacuum, like this lambda less than 0 vacuum here with this big crunch. And so it will span a finite causal diamond, which is this black thing here. And as you see, by focusing on this causal diamond, I've basically eliminated almost all of the space-time, and these infinities are pretty much gone. So let me zoom in on the diamond. The picture is now significantly simpler. What we see is essentially a sequence of tunnelings, a particular decay chain through the landscape, where I start out in some vacuum, I jump around, usually downward in cosmological constant, until I reach one of these terminal vacua, and then the game is over. And this is a finite problem. The probability of some vacuum X to be produced is just a probability that, let's say, the green vacuum is going to show up in this decay chain. In a typical situation, you will have 10 to the hundreds of vacua, and such a decay chain will be a few hundred vacua long. So you have to compute this probability, but this is completely straightforward. from branching ratios. You're in, let's say, the blue vacuum. Well, where are you going to go next? To the green one with 90%, to the red one with 10%. These are numbers that we can compute from gravitational instantons fairly straightforwardly, given information about the theory. And that from those branching ratios, I can compute the total probability of going through the green vacuum or reaching the green vacuum by just summing over all possible paths that would take me there. And there's a simple formula that sums this up. Here eta is this matrix of branching ratios from any vacuum to any other vacuum, and P is a vector with one entry for each vacuum, the probability of this vacuum to be produced. P0 encodes the initial conditions, and I will say more about the dependence on initial conditions when I go through the specific example in a minute. Now, this is a nice formula, but it's not very practical. If you have a landscape with 10 to the hundreds of vacua, these matrices are large. And you're also not interested in the probability for one particular vacuum. You want to average over lots of vacua with similar properties. And so what's more useful is to actually run decay chains on your computer, sort of Monte Carlo method. You let the computer decide in any given vacuum where it's going to go next according to these branching ratios, according to the relative probability to go next to various different places. And just generate these decay chains and see where they lead you to, what kind of vacua they produce and which they don't. We haven't attempted to apply this to a realistic landscape. I'm not even sure that we have enough statistics yet for that to give us a credible result. But we've applied it to a toy landscape, and we're going to learn some lessons, I think, about how strong cosmological selection can be just from that. It's not a toy landscape in the sense of being smaller than the string landscape. It's one with a realistic number of vacua, 10 to the hundreds. It's essentially the model that Joe and I proposed a number of years ago, in which you hold some internal manifold completely fixed. There's no back reaction. There are hundreds, let's say 250 for definiteness, four-form fluxes in 4 dimensions that are sourced by membranes with charges not much less than 1, which you can get by wrapping higher dimensional branes on cycles. And these fluxes give you a contribution to the cosmological constant that can be represented as a radius squared in this 250-dimensional flux grid, of which I'm, of course, drawing only 2 dimensions. So I'm assuming a negative natural bare cosmological constant. Then the vacua inside this green circle will have negative lambda. Then this green shell here is supposed to represent the Weinberg shell, where we're very close to 0. Here are positive values, and this is the region where the value is greater than 1 in Planck units. So we should probably exclude that because semi-classical treatments break down here. And of course, the point of this model was to show that string theory has the kind of complexity in it and has the vacuum structure in it to be capable of solving the cosmological constant problem. In other words, the density of vacua on the scale of the cosmological constant is sufficiently high that there will be some vacua in this green shell. So the kind of questions that we want to ask about this model are, well, the most straightforward thing is, how many vacua are there in this Weinberg shell? How many vacua have cosmological constant like ours? And then a little more refined, perhaps, if I restrict to this ensemble of vacua, what are their properties going to be? Well, in this toy model, the only thing I can really ask about is what are their fluxes going to be like? Each of them is characterized by 250 fluxes, so we should be able to specify 250 probability distributions over integers that characterize typical values of these fluxes in this ensemble. And it's perhaps clearest to first ask these questions, forgetting about cosmological selection, just really looking at the raw landscape, and then ask them again with cosmological dynamics, take into account according to the prescription that I formulated a little while ago. So in the raw landscape, well, Joe and I had a formula for estimating the number of vacua in the Weinberg shell, which is quite good if the fluxes are typically large. But in the most natural models, the fluxes are of order 1, and the formula is not so good, and in any case we want maybe higher accuracy here because we're trying to compare selection to no selection and see quantitatively what it actually does. And in that case, it turns out that it is better to start the other way around and to first try to answer the question of what the probability distribution of fluxes is, and then derive the number from that. Okay. You can get the probability distribution by defining a canonical ensemble of vacua. You just formally treat the cosmological constant like an energy, define a dual temperature, adjust it to the value so that the expectation value of lambda is about 0. And that gives you an ensemble in which you can compute the probability for the ith flux to have value n by just a Boltzmann factor. Okay, this thing inside the Boltzmann factor, this analog of the energy, is the contribution that the ith flux would make to the cosmological constant if it had value n. And so you get this very nice probability distribution, well, 250 of them actually. And you get that first, and then from that you can compute a Shannon entropy and exponentiate that, which for the usual reasons gives you basically the effective number of states, or in this case vacua, in this ensemble. This distribution will be spread over quite a big interval in lambda space, but it's then trivial to project onto the Weinberg window and figure out how many of these states are in the Weinberg window. And these are the results. I'm not going to show you 250 probability distributions, but 6 of them. And what you see is that, remember, the I equals 1 flux is the one with the smallest charge. This one has the largest charge membrane. So this one contributes less per unit flux to the cosmological constant. And as a result, the distribution is wider. You tend to have larger fluxes over here and smaller ones over there, where each unit of flux contributes more to the cosmological constant. And computing the Shannon entropy and exponentiating, projecting gives you 10 to the 121 vacua in the Weinberg window. This 121 here is a coincidence. It has nothing to do with this. There's just a lot of vacua, so you can easily solve the CC problem. This is overkill. Now to cosmological selection, and let's see what it does to these distributions and to this number. So what we do is, first of all, we have the problem of initial conditions, which is really 2 problems. One is deciding what reasonable initial conditions should be for our universe, and my guess is probably no better than yours. And then actually implementing them. Well, as for the decision, fortunately, it turns out that it doesn't matter very much for our answer. The only thing that we mustn't do is we would have a problem if there was some strong preference to start with small or negative lambda. And in fact, that would be a problem in almost all scenarios that I can think of. So as long as you start, for example, with a completely random vacuum, well, this is a very high-dimensional grid, so the volume grows very rapidly as you go out. So you're very likely to pick one that's out at large radius, at large lambda. Or you could use Andre's or Alex Vilenkin's prescriptions, which also push you towards large lambda. Whatever you do, the important thing is that you implement this in a direction-independent way, which is not so trivial. So you want to pick a random vacuum in a way that's not biased towards one of the axes. And again, this canonical ensemble helps you that I talked about earlier. You just want to crank up the temperature so that the expected value of the cosmological constant is now up here. And then you can pick from that distribution and have your computer start with that vacuum. And then compute the various decay probabilities into different directions. And we know how to do this from instantons, and have the computer pick a particular direction and do this over and over again and generate this random chain until you're close to lambda equals 0. You don't have to be on the Weinberg shell. It's the same statistics apply if you're just more or less one step away from 0, which is a much wider shell, but still small compared to this distance. And you record the final J tuple, the 250 integers that characterize the final flux configuration. And then you just do the same thing over and over again. You pick some starting point, you run a decay chain, you record. You do this a few thousand times, you get very good statistics for these probabilities pi of n. And here's what they look like. So they're shown here in red, and the blue ones are the old ones without cosmological selection that you saw earlier for comparison. what you see are fairly sharp contrasts, especially out here on the small charge fluxes, which used to be all over the place and now are almost certainly turned off. Okay. Generally, the distribution has narrowed, and because we have hundreds of probability distributions, we can make a lot of predictions. We can combine them, for example, into statements that we can make with probability very close to 1, which are the most useful statements in a situation where you get to observe only once. So those are the predictions you need to make in order to be falsifiable. Examples are, well, the first 30 fluxes after cosmological selection are almost certainly all going to be less than or equal to 2 with some probability greater than 99%. There are going to be no fluxes at all greater than 4. And I've picked these examples because they happen to contrast completely with the naive intuition that you would have gotten just from the raw landscape statistics. The exact opposite would have been overwhelmingly likely without cosmological selection. So it's a very nice, it's nice to see that this really has important effects. To quantify the overall strength of selection effects, we can again take these probability distributions, compute in entropy, and find that only 10 to the 80 vacua in the Weinberg shell are effectively accessed by cosmology. So we started with 10 to the 121. So out of 10 to the 41 vacua, only 1 is really found by these decay chains. It's a very strong selection, and this is quite generic. This is not particular to this model. So that's why we can get a lot of extra predictions. If you're interested in why these particular things are happening from the blue to the red distribution, well, it has to do with the fact that stuff that's unstable decays early on in the decay chain. It will not be observed, and in this model, the things that are unstable, here are lines of equal decay probability, and the decay gets more likely as I go up here. Large fluxes, 8, 7, 6, they get killed off immediately. Fluxes associated with small charges, those membranes are easy to produce. Those get killed off. That's why you're seeing no large fluxes. That's why you're seeing this flux over here turned off. And of course, this general property is something that I would expect to be true more generally beyond this toy model. I should emphasize again, these predictions are toy predictions. Okay, but we can learn general things. Cosmological selection really can thin out the landscape by enormous factors, suppress large classes of vacua, and give you strong predictions. And some models can be, in fact, ruled out by cosmological selection. If you started with enough vacua to solve the CC problem, you might end up with not enough after cosmological selection. However, this problem is not a generic one. Vilenkin has exhibited situations where other measures seem to basically rule out all landscapes because the cosmological selection is too strong. Okay, so let me say a few words about entropic selection effects, or entropic. I hope this will become clear in the context of this causal diamond picture. Here the basic question is what the probability is for some vacuum to be observed, not just produced. And the standard approach seems to be to weight the vacuum by the number of observers it contains, or maybe observations, which in the global picture is already a little problematic because it will contain either 0 or infinitely many observers, since it's an infinite FRW universe. In the causal diamond, you only get to count the ones that are inside the diamond, which is basically inside the cosmological horizon. So that number is clearly finite, so you've already made your life easier. You still have the standard uncomfortable question of what actually constitutes an observer or observation, which becomes most important when we want to explore the landscape far away from our own vacuum. And what we've proposed is to trade observers for a much cruder but much more sharply defined quantity, and I'll try to convince you that this quantity delta S is actually an extremely good proxy, perhaps surprisingly good proxy for observers. The rationale is that observation, whatever else you think about it, requires free energy. You have to be able to store, retrieve information, to do computation. That's not going to happen if you're completely thermalized. And so you might conjecture that the total amount of entropy that's produced in the universe is some measure of its complexity. Of course, that's a conjecture. Not every bit of entropy that's produced is produced by us thinking or whatever, but at least on average, you might expect that the number of observers scales like delta S. And more precisely, we've defined delta S for some vacuum X to be the total amount of matter entropy, excluding black holes, produced inside the causal diamond. Which again will be finite because, let's say in our vacuum we have a positive cosmological constant. After a while everything gets emptied out when lambda takes over. So this will be certainly finite since reheating. Okay, so then we weight by delta S. We multiply all the probabilities that we got from the previous calculations by this delta S and get a new distribution that we would still have to normalize. What question can we apply this to? Well, the standard one, let's say. What is the probability distribution for lambda? And I'm going to also make the standard simplification of restricting to the subset of the landscape. Could now be the actual string landscape with low energy physics identical to ours. Only lambda varies. It's legitimate. It's just not all that we want to do. But if I got a bad prediction already at this stage, then I would have a problem. So by entropic weighting, we get, well, usually we compute dp over d log lambda, so we have a factor of lambda that reminds us that there are more vacua out at large lambda than at small lambda, and then this is the weighting factor, delta S, how much entropy to be produced as a function of lambda, and this is an astrophysics problem. That's what we need to compute now, and it's actually, you know, it's a fairly involved computation, and I'm not going to have time to show it to you. I'll just show you the final result, which is this probability distribution here. The dark curve, shaded regions leave out a 1 sigma region, and the observed value is well within that. Of course, the only thing we really care about is that it's not really at some suppressed place. Okay, and so our lambda is very typical. It's a wonderful match under this distribution, and I should emphasize that this really wasn't clear to us before we started. And just for comparison, this is the curve that you would get, this dashed curve, by the standard approach of weighting by the number of observers per baryon and making the assumption, the extra assumption that we don't make, that observers need galaxies, and if you're happy with any old galaxy, then this is what the probability distribution looks like. Lambda wants to be 1,000 times larger, and the favored value is the observed value is very suppressed. So where does this come from? Well, lambda still wants to be large by raw landscape statistics, but lambda should not dominate too early, because once it dominates, it empties out the causal diamond completely, and you don't get to produce entropy in it, or have observers in it, if you want to use that. And so the compromise between these two requirements is that the preferred lambda is basically one where lambda starts to dominate just after you've produced most of your entropy. And then you can kick out all the stuff from the diamond. So right there you've solved the coincidence problem. It's not surprising that we live around the time when lambda is starting to dominate. When you put in numbers, well, you have to work out when entropy production actually peaks in the universe. It's at some time of order 10 to the 10 years, and that's 10 to the 61 or 2 in Planck units, which is where this number 10 to the minus 123 comes from. So that's why this agreement is so good. Galaxy formation plays absolutely no role in suppressing large lambda in this approach. And that's why we're very optimistic that once we include more variables such as delta O over rho, we're not going to have, for example, the standard problem of being pushed towards extremely large values of lambda by helping galaxies form by making delta rho over rho larger. The other thing that makes us optimistic for that situation is that delta S turns out to be dominated, and this curve, where did it come from? Well, it actually comes from infrared radiation emitted by dust heated by starlight. That's fantastic. It means that delta S knows about things that we usually put in by hand. You take away heavy elements, it will immediately go down because dust doesn't reprocess to the infrared. Take away stars, galaxies, it will go down. But you didn't put that in. It seems to know about that. Okay, so that suggests that when we explore larger portions of the landscape, delta S will really be a useful tool and something that's always well defined. So let me put up this summary and take questions. Thank you.
Eva, please.
So you mentioned your results were insensitive to initial conditions. Was that a result of the calculation, or do you have intuition for why that happened?
It's not completely insensitive. I should emphasize this again. You can certainly find initial conditions which will change this result significantly. It's just that there's really a fairly large class. I mean, in some sense, the ones that change it look fine-tuned, and the ones to which it's insensitive are sort of generic. The reason for this is that selection effects really start coming in when you, let me go back to this, here, yeah. So early on in the decay chain, the decay is fairly random. Okay, there's no real selection going on here, because the decays are unsuppressed, and so the probability to go here and there, they're all not that small. But further down, the probability to decay at all, I mean the decay per unit time, which doesn't really end in this calculation, it tends to be enormously small. And so you're comparing the probability to go this way, which is e to the minus 200, with the probability to go that way, which is e to the minus 300 or whatever. And so the differences are large, so the branching ratios will look like, well, pretty much 1, 0, 0, 0. So down here, you effectively have preferred paths, and things flow together and you get selection. But most vacua start out up here, and so they naturally flow into this region and then get processed by the selection effects down there.
Sandeep?
Hi. Something I didn't understand was, along one of these chains that you described, I imagine sometimes you just miss out on a small enough value of lambda. That is, you go from a bigger one to ADS space directly.
You always do, in a realistic, because this set of vacua has some fraction 10 to the minus hundredths of the total set, so I'd have to run a lot of decay chains before I hit one of them. But the point is that the statistics of flux distributions is going to be the same whether I choose this extremely thin shell or I enlarge the sample, as long as I don't enlarge it too much. I shouldn't make this shell wider than what corresponds to the difference of one flux changing. Okay? Because then it's sort of manifestly clear that the probability distributions of the fluxes can't be very different in this larger ensemble and in this smaller ensemble. And what our decay chain naturally does, it will find a vacuum with the last positive cosmological constant. And that's really the one that we use as our endpoint. We could have also used the one with the first negative cosmological constant. It really would have made no difference, and that's what we checked explicitly, that it really doesn't make a difference. So if we had evaluated the flux probabilities on some much larger shell, that would have changed the answer. But just enlarging this Weinberg shell to be big enough to capture these chains as they go through is not something that affects the result. We just have to take care when we compute the number of vacua in the Weinberg shell that we remember to project back onto that very thin region after we compute the number in the total ensemble.
I see. Fernando?
Why the entropy is dominated by a star and dust instead of black holes?
Because I said that I explicitly exclude black holes. Now, I'm allowed to do that because I'm just trying to find a proxy for observers. Look, I'm excluding black holes. That's a lot better than saying, I want heavy elements, I want carbon, I want stars, I want galaxies. I'm just saying, compute the matter entropy that's produced. Don't ask me why. Well, why? Because I don't think black holes have anything to do with observers. But it's my best guess at a well-defined quantity, at least in the semi-classical regime, that's sharp, and that can be computed in vacua very different from ours, at least in principle, and that seems to capture what observers need rather well.
There seems to be a hand behind you. There. Yeah.
So I'm not sure I understand correctly, but you're saying that most of the entropy come from starlight heating dust, but then in your calculation you say this does not depend on the growth of perturbation. So how can that be? I mean, you got to form stars.
Yeah.
And that depends on the growth of perturbation.
Right. So what we did is we varied only lambda for now. Okay? And when you look at, sorry, let me go to this graph. Here we go. So of course it is true that if I make lambda really large and I disrupt the formation of galaxies, that will suppress entropy production, and that will be registered in this curve. But the point is that it's registered only out here at this tail. There's something else that made this curve go down long before lambda got large enough to disrupt galaxy formation. And that something else is this effect that I talked about, that with lambda, let's say at this value, lambda starts dominating the evolution of the universe at a time when stars produce most of their entropy, when most observers are actually around. And it expels these entropy producers. It expels the free energy that you're trying to harvest. And that is the most important effect in this particular situation where we're varying lambda. That kicks in first, and then whether or not you include some Press-Schlechter factor for whether galaxies form or not, that actually turns out to not even be very important in this situation. But if I started asking about other variables, such as delta rho over rho, and there's lots of other stuff we could ask, the baryon to photon fraction and so on. That's where I find it just intriguing and well, somewhat confidence-inspiring that delta S seems to know about these things. So as I said, if I take away heavy elements, which is not something I'm doing here, then delta S would immediately drop by a factor of 100 because they are the things that take every optical photon and convert it to 100 infrared photons. And so it's sensitive. It happens to be sensitive to that.
I'm sorry, we are instructed to make a cut of the discussion. So let's thank again Raphael.
Thank you.